Okay, I will start in 5 minutes time. Thank you. Okay, good morning to all of you. Sorry for delay because of my network issues. Luckily, it was resolved. Okay, now we get started. Okay, we continue from where we stopped, and probably this will be your last topic for AA, analog application. All right. Okay, now this topic will be on operational amplifiers, okay, which is one of the very popular topic where questions will come from during the exams. Okay, so maybe I need some of your attention. Okay, all right. If no other things, I will get started now. All right. Op-amp, I think the short form they call op-amp. Okay, actually it stands for operational amplifier. All right. It's very common when people say op-amp. Actually, again, I say refer to operational amplifier. So basically, the name itself tell you something about this device or component. Amplifier means something like you improve or increase the signal strength, for example. All right, a small input and then the output is much larger. Simply put, okay. So okay, over here they didn't really mention about the application, but actually there are plenty of application for an op amp. All right. Further down, we'll discuss the different circuits that can be connected for different users. Okay, first thing first, very important to draw your attention. This symbol is drawn for an operational amp. Okay, this is an op amp symbol. All right. First thing you need to know is these two terminal, which we call inverting and non-inverting. All right. Which is written here, inverting and non-inverting. All right. Now, of course, inverting here means it's going to a negative sign. All right, connection wise. And non-inverting, okay, we take it as a positive sign. All right. Later, further down, you will see the difference between these two. All right. Why is one known as inverting? Why the other one is known as non-inverting? All right. Okay. They also have dual power supply, which means you can see a positive supply voltage and also a negative supply voltage, which is not common, but in operation M they do exist. Although sometimes you still have operational M with one power supply source. Okay, just take note, dual polarity power supply. Okay. Then of course, obviously you have only one output, all right, which is over here. Okay. Now, an op amp will most of the time come in this package like this. Okay. Rather small IC, I call it, because there's only 8 pins. All right. From 1 to 8. Okay, 4 on each side. So it's basically an IC in its own form. All right. When you start to use it during your so-called lab session, you will see this component. The most common one is the LM318, a general purpose op amp, which I think we likely to use during our practical session. All right. Okay. Just to confirm one more time. I think all you can still hear me, right? Okay. Okay, thank you very much. So I will move on from here. All right, basic op amp operation, the basic operation. Okay, as mentioned just now, they have two inputs. One is the negative, which we call inverting. The other one positive, we call non-inverting. All right. Now, then we talk about, of course, application, okay, of the op amp. Here, they call linear operation application. What does it mean? Okay, most of the time, when the output signal changes with proportion to change of the input signal. All right. Example, later further down, we'll see all these inverting amplifiers, non-inverting, adders, and subtractors. Okay, further down, we'll see some of these application. All right. For now, just take it that these are the application for linear application. Of course, they also have non-linear application, which also we saw so far. This is one of them, the comparator. Remember when we are doing those so-called switching power supply. All right, this one sine wave or wave converter, also from sine wave to square wave, and the recent one that we talk about. The last lesson, remember all the multi vibrators, the 3 types: a stable, monostable, and bistable. Okay, so this type of so-called application, they are non-linear because they're different states. All right, not only just one state. That's the reason. Or they call non-linear application. So take note, just in case they ask for application or non-linear application of an op amp. So any one of, or at least remember 2 of it. Okay. Okay, not then we now go right into it and see how this op amp works. Okay, we will start to analyze a bit. Okay. All right. First thing, there are some assumptions to be made first before we start to talk about it. All right. So first thing is they say there's no current flows to the input terminals of the op amp. All right. Okay. Then the voltage at the inverting output, or rather the input, is always equal to the voltage at the non-inverting output. So in other words, this point over here and the voltage over here, both are similar. That's assumption first, assumption. Okay, assumption, no change. All right. Then the second point here is the output voltage, VO. VO is over here, the output. All right, is out of phase to your V in, your input. All right, okay. So obviously you see the phase change here. If you look at the output waveform, right, which is 180 degrees out of phase. In other words, when this is positive, on the positive half, your output goes to the negative half. All right, and of course the opposite. Negative half becomes a positive half. Okay, so basically it's 180 degrees out of phase. Take note, because now your input is connected, so to speak, to the inverting input. Inverting input, be careful. All right. Okay. So over here, that's what I just explained. 180 degrees out of phase between the input voltage or input waveform and the output waveform. Okay, please take note. And because it's connected to the inverting input. Right, then move on. So this is the first op-amp we are talking about, which we call the inverting op-amp circuit. Okay, this is the main thing. Important, I want you to take note. Input going to the inverting point or the input. Okay, so the name of this op-amp comes from this. Okay, the main thing, so that you were able to recognize further down when you call it inverting or not. Okay, now then after that you have some little formula here to calculate the output voltage. All right, so the output voltage here is given by this simple formula here, which is RF. RF is a feedback, it stands for feedback resistor, and the RI is the input resistor. Yeah, so the feedback resistor divided by input resistor multiply by your input will give you your output voltage. Okay, now you can see a minus sign here just to highlight to you. Right, again, because your input is going to this negative or inverting input. All right, that's why the negative sign is there. And also to tell you that they are 180 degrees out of phase, just now mentioned. Okay, so in case some of you are, how come there's a minus sign there? Okay, I repeat, because first you're going to the inverting input, the negative side here, right? And also the waveform is 180 degrees out of phase, just now above here mentioned. Point number 6.1. Okay, so that's it for this calculating of the output voltage. Okay, nothing difficult, but remember it because in the exam you may need to ask so-called to find the output voltage for inverting op-amp. Okay. Okay, apart from the voltage, we are also interested in the gain, which we of course we are interested because this is an amplifier, right? So we are interested in how much the signal has gained, so to speak. So the gain is given by A is a letter to signify gain. V is a voltage. So this voltage gain is AV. All right, it's given by V out over V in or RF over R1. Okay, Ken? So you can calculate the gain by using this simple formula here. Any question up to now? Any question? No? Okay, no question. I move on to look at an example how to do some simple calculation for the inverting op-amp. Okay. Excuse me. Okay, this circuit is given to you. First thing, recognize it. The input, voltage, where is it going to? Going to the negative point or input of the amplifier op-amp. So you know straight away that this is an inverting op-amp. Okay, first thing, so that followed by all your calculation, you're on track. Okay, so R2 is the feedback resistor. R1 is the input resistor. We got RI, this one RF, RI, but here they put R1 and 2. Okay, so the solution is, of course, using the formula just now we have just seen. to calculate the output voltage, right? You want to calculate the output voltage. And then this is the formula given just now before we come to this example. So just put in the value accordingly. RF, which is remember the feedback resistor. You can see the loop here. All right. This is a feedback resistor. R2, don't confuse. Because if you put R1 as the value, then the whole equation, or rather the answer will be wrong. So R2 is the RF, okay, which is seen here. They put RF. So remember, RF is a feedback resistor. And then Ri is the input resistor, okay, which is R1 over here. So 10K over 2.2, very obvious. You can see the value given multiplied by an input of 1.5 volts. And please do not forget to put this negative sign here. Right? Okay, very important. If you don't put this sign here, your answer is wrong. It's not positive 6.82 volts. It's negative 6.82 volts. Okay, so yes, be careful of that. That's why I emphasize to you that it's going to the negative input of the op amp. All right. After calculating the voltage, or rather the output voltage, you want to calculate the gain. Okay, the gain is given as above, V out over V in, or RF over R2, and then you get the gain. All right. Also, there is a negative. Right. Now, gain has no units, so it's just a number. All right. Can I pause for a very short while, for 1-2 minutes. If you have anything you want to clarify, you let me know. Anybody? For this example, for inverting operation M or op M, any part of the calculation you're not sure, or which value to put in? Anyone? Okay, no question, then I will continue from here. Okay, so this is a good example of a calculation for inverting op amp. Okay, important thing here to me, I just mentioned to you, look at the input where it's going first. All right, because if it's connected to positive, it will be totally different. So now we're talking about inverting. So it should be going to the negative. Okay, so you identify it as a inverting op amp. Okay, so no question, we move on. Okay, any question? If not, I pause for 2 minutes. And then I will continue with the non-inverting op amp. Okay, thank you. Hold on. I think one of the managers is calling me something urgent. Just give me 1 minute or so. I will continue from here. Thank you. Okay, I will continue from where we stop. Okay, so the next one, we are talking about non-inverting. Be careful, just now the one was inverting, now non-inverting. So why I purposely circle? Because I want all you to pay attention to this. Because if you confuse the two, all the calculation will be different. Okay, I start again, non-inverting. So the moment you see non-inverting, you must always tell yourself the input is going to the positive of the op amp. This one must be correct first before we talk about the rest. Okay, Ken, one more time. Non-inverting op amp, the input VI, the input voltage will go to the positive input of the op amp. Okay, and of course now you realize, also observe something different. You look at the input waveform and the output waveform. They are not out of phase. They are not out of phase. They are in phase. Okay? In phase means if the positive half goes in, the output also the positive half. Okay? And same for the negative half. Alright, so there is no out of phase here. It's in phase. And I go very slow because this one important, so that you don't confuse with the other one. Alright. Can. So the resistor as usual connected, there's one feedback and then one R input going to the ground here. Okay, this is still RF now. Okay, the feedback resistor, and this is considered the input resistor, RI. Okay, still the same, just the position only. All right, if there's no question regarding what I just shown you or ask you to take note, we move on to the formulas. Okay, here now slightly different. You want to calculate the output voltage, you will have this formula for you. All right, 1 plus RF over RI multiplied by the VI, the input voltage. Okay. Also, this is a formula given to you. Okay, or if you want to move the VO over VI also can, then it will become the next one. Okay, you look carefully, the next one is voltage gain. Okay, most of the time are always given by V out over V in. All right. Then you have 1 plus RF over RI. Now, if you look carefully at the top formula here, if I move the VI over, it is, or rather, for example, I show you this one, if I move over here to the left-hand side, sorry, then it will become the VO over VI, correct? Then on the right-hand side, I'm only left with 1 plus RF over RI. That's why they show this one. It's actually the same thing. It's just a movement of the term. Okay, I hope you can see it. All right. Then any question on these two formulas? One for calculating output voltage and one for calculating the voltage gain. All right, gain has no unit. Of course, voltage is still in volts a unit. All right. Okay, if no question, then I move to an example to help you understand better how to apply the formulas. Okay, let's take a look at example 2. Before I start again, I keep repeating because I want you to remember your input. Always look for input voltage, where it is going first. You say, okay, it's going to the positive or the plus sign of the op amp. Then you are very safe to say that this is a non-inverting op amp circuit. First thing, very important. I keep repeating because no choice. I want you to remember until the day you take your exam, right? So that you don't confuse. Okay, so input VI 1 volt goes to the positive side of the op amp, and that is known as non-inverting op amp. Okay, then you see R2 here, which is the feedback resistor. You can see the connection from output going back to the input. You know that this is the RF or your feedback resistor. Okay, And then you have your R1 here, which is your input resistor. Okay, 1K there. And so if you have identified all this correctly, then you move on to do your calculation with the formula. So it's not about quickly getting the answer. It's about identifying the right components and the right values so that you get the right answer. Okay, so formula given just now like this one, VO is 1 plus RF over RI, identify feedback resistor, which is R2, 9K, correct? And then input resistor, 1K, correct? And then of course you do your calculation and you get example 10 volts, right? So important, I still want to stress, get your component value correct, don't confuse. Can you imagine if your RF and RI, the value inverted or confused, become 1K over 9K, your answer, you won't get 10 volts. That's what I mean. Okay, I hope you have to pay attention to this, no choice. Okay, so just identify one more time, R2 is a RF, R1 here is a RI, which is an input resistance. Okay, this is actually shown here. Okay, RF. In case some of you, how come they never write the R1 and 2? Actually, it's the same. Okay? And then you get your voltage at 10 volts. Then you go on to calculate your gain, voltage gain, AV. Okay, given by V out over V in or 1 plus RF over RI. So we use this formula, the same thing you plug in, actually this whole thing is coming from here. Yeah, all right. And then you get a gain of 10. Now gain don't have any units. Please take note, no units, just a number. Okay? So you can say that if I put in 1 volts, my output will be 10 times more. That means 10 volts. Okay, which is correct. You look carefully. 10 volts what? Because my input is 1 volt. Because my gain is 10 times, right? So 10 times 1 volt will give me 10 volts. Makes sense, right? I pause for a short while. I hope if you have question, you ask me. Any question, I will wait for you for 1 minute. If not, then I move on. Thank you. Any question for me regarding the example 2? Okay, no question, we continue. All right. That will be the example for non-inverting op-amp. Okay, now we move on to more application of op-amp. Just how we saw right in the beginning, different application. Now we are moving to some of the application here. That means can be used in different scenario or application. Okay, the next one we can call it a summing amplifier, or just now further up we say it's an adder. All right. Okay. So okay, first before we start, this is how the summing amplifier looks. I mean, in terms of the connection. Okay, first thing, identify again where are all the inputs going to. It's going to the positive or negative, and you realize it's going to the negative input of the op-amp. Okay, the positive is going to ground. Okay, so RF is here as usual. This is a feedback resistor. R1, 2, and R3 are all the input resistors. Okay, then your output as usual over here, right? Okay, so this is the adder or summing amplifier we call. So you can add, they tell you that you can add 2 or more input. Okay, so here, over here, we have 3 paths, right? V1, V2, V3. Okay, All right, so we move on now to do some simple calculation with the formula. First thing first, this is a formula to calculate the output voltage. Okay, output voltage. Yeah, V out, output voltage. Okay, before I start, just now I remind all of you, why is there a negative sign here? I want to point out to you again, why is there a negative sign there? That's how I mentioned already. I hope you are paying attention to this thing because it's important to you. With the minus sign, without the minus sign, the answer is totally different. And yeah, so that's why I keep repeating. Okay, if you have not catch it just now, listen again. The negative sign is because all your input is going to the negative input of the op amp over here. Okay, so your output signal will also be out of phase, which we also mentioned just now. In case some of you miss it, okay, let's say your input here is this, right? But your output will be out of phase. Okay? Because of the inverting input. Okay, any question? Okay, you know I continue. So this is the formula. Minus RF is the input resistor, then bracket, close bracket, the V over R. Okay, if you realize that this will give you the I, right? Okay, V over R in ohms law is current calculating. So each of the formula here, V2 over R2 are calculating the currents. And finally, all the current multiplied by your resistor will give you the voltage. This is Ohm's law. Okay? All right. Then they say something. What if all the input are the same values? Resistor all same value, what happens? Then you will get all this, or rather R1, R2, R3 is equal, then it becomes an R, same value. The formula become more simplified. Be careful, there's a condition here I just mentioned. Provided the three resistors are all equal or of the same value, then your formula becomes like this. Okay? Can? No question, we move on. One more condition, they say, what if the feedback resistor also same value as all the input resistor? So this part of it becomes a 1, right? If both are the same value, it becomes a 1. So that's how you get VO equals to minus close bracket V1 plus V2 plus V3. That is this condition. If all the resistors, including the feedback resistors, are the same, then your output will be a very straightforward answer. All right, just V1 plus V2 plus V3. And then don't forget about your negative sign is still there. Doesn't change, Okay? So it's just the sum of the input voltages. Okay? That's why they wrote here. All right, can we move on? Okay, now I think it's good to look at an example. Before we look at the example, they tell you one very common application of the summing circuit or adders, which is your D to analog converters, right? I think some of you have seen this. Sometimes they write it as DAC, DA and C. Okay, digital to analog converters. It's very common. Okay, that's one application of an adders. Okay, now we take a look at example 3. All right, to do some calculation. Now, don't rush to do it first, but rather look at what is given to you. All right, here they say the R1, R2, R3 are the same value. Okay, but not RF. Be careful, RF is 10K ohm. Okay, take note. So V1, V2, V3 voltages are given accordingly. So if you want to solve this output voltage, we go back to the formula, which is this one. Okay, just now before you come here. Again, before when you write out the formula, don't forget the negative sign. Okay, because it's a inverting. So we plug in the value accordingly. This will be your RF. All right. The feedback resistor value 10K, and the rest all the 2K here, because they tell you R1, R2, R3 is the same. Right, and then you have negative 3.5 volts. Okay, I still emphasize. Okay, don't forget, please don't forget to write the negative sign. Because without negative sign, it becomes 3.5 volt and the answer is incorrect. Okay? Okay. Any question? I pause for a short while in case you want to clarify any part of the calculation for the summing circuit. Any question? Okay, no question. We move on. All right. We have finished the summing. Now we go to the difference amplifier. Just now that one called adder. Now this one called subtractor or difference amplifier. Okay, it meant the same thing. Okay, and this is the connection of the difference amplifier or subtractor. Okay, something different. So you realize that the input signal does goes to the negative and as well as to the positive. So what happened? Very interesting. Just sound quite obvious. Only the one input go to either negative or positive input of the op amp. But now the input voltage goes to the negative input, and the input voltage also goes to the positive side. So you want to find out what happened. Okay, this one no change. R2, it's quite obvious. Output goes back to the input. This is also always known as the RF. Although here they put R2 here at the moment. Okay, can Okay, let's take a look. All right. First thing they say have input voltage apply. I just mentioned apply simultaneously to both. Just mentioned to the inverting and non-inverting. Okay, which is here inverting and non-inverting. That's what they mean. It's just I just spoken. Then what is the output voltage now? It's given by VO R2 over R1 close bracket V2 minus V1. Okay, so this is the formula to calculate the output voltage for a difference amplifier. Then, so R2, remember this is your feedback resistor. Okay, R1 is a resistor that is at the input. Okay, over here. And then V2 minus V1. Now, why V2 minus V1? Because V2 is at the positive terminal. Okay, and V1 at the negative terminal. That's why it's V2 minus V1. And so at the moment, there's no negative sign in front of the formula, so don't add in. Okay, we move on. Now they say what happened if R2 equals to R1? Then very obvious. This whole thing becomes a 1, and then you are left with V2 plus V1. That will be your output voltage. Okay, because if both are equal, you cancel out. You cancel out, only you left with this V2 minus V1. Okay, which is from here. Yeah. Okay. Of course, the condition here is R2 equals to R1. Both resistors are equal. All right. Can I hope you can see that. If not, then please let me know. This one I already mentioned to you, YV2 minus V1. Here also they write there to the non-inverting. Okay. But of course, if it's reversed, then you also have to change accordingly. Depends which one. Then, just to clarify this point. Okay, any question first before we look at examples? Any question up to now? Or regarding this difference amplifier or subtractor? No question? Okay, can move on. If no question, we come to the comparator. Okay. I think we have seen this one in the switching circuit before, right? Where we use a comparator, remember, to compare voltage from the output and feedback to the input to make changes to the input. Okay, so now we are looking right inside this comparator here. Of course, first, before we start, they say comparator compare two voltages and provide a large output signal when two inputs are not equal. Okay, right? For an ideal op-amp, they always say the output always equal to the supply, not equal to the input. Take note. That is for ideal case. Ideal. Okay, but of course, when you start to connect other components and so on, it's not the ideal condition. They're just stating out to you. Okay, so wait, before we continue, this is your comparator circuit. Okay, so when you hear the word comparator, you know that you're going to compare the two input signals, so to speak, okay, that is coming into the comparator, okay, which is two input here. All right, one is a negative, one is a positive. And then let's see what happened now. There's a condition one. Okay, we'll start now. Okay, so if the voltage of the non-inverting input terminal is greater, we're talking non-inverter means this one. Okay, the positive is greater than the inverting. The output voltage equals to positive Vs. Okay, this is the condition. Because now we are comparing. Okay, after comparing, then you decide what you want to appear at the output voltage. Here they tell you that if this condition is fulfilled, then the output voltage is V out equal to Vs. Okay, V out here. That means this voltage will actually appear here, the Vs. Okay, this is the condition. All right. The positive terminal voltage here is greater than the voltage at the negative input of the amp. All right, this condition must be fulfilled. Then this will happen. All right, because when you have comparator, you need to compare. So that is a condition. Okay, if this positive greater than the negative input, output straight away is the supply voltage, which is over here. Okay, then next thing, what happened? The other way around, they say that if the non-inverting terminal voltage is less than the voltage of the inverting input terminal, the V out equals to negative Vs. Okay, so now this is another condition, right? Oh, this condition must be fulfilled first. Then now V out equals to negative Vs. Be careful, negative, not positive, negative. Okay, so there are basically two conditions, all right, to determine the output. So in other words, your output can be Vs or negative Vs. Yeah. Okay. Yeah. So if your output is positive Vs, then you are applying this condition to get this output. If your output is negative Vs, then you are applying this condition. Okay, so please take note of this. Could be a potential question in your exam. All right, so be careful again. The output, one is negative, one is positive, but depends on the condition. Okay. Any question up to now? Just give a quick check. Any question regarding the comparator? So to summarize this comparator, basically output voltage of the Vs depending on the input condition of the two voltages, right? Okay, so if each condition is met, the output will follow accordingly, giving you a positive Vs or a negative Vs as the output. Right? Any question? If no question, we look at the example and see we can understand better. Okay, so this is an example of a comparator. Hopefully, it'll give you better so-called understanding after looking at the example. Huh? All right. First, before we start, of course, always remember what is given first is important. All right. This is a VE. This one now I call it a VREF. Huh? Okay, nothing wrong. Huh? Comparator, we can have a reference voltage. Okay, so you're comparing VI with reference voltage all the time. Okay, when you compare with something, you must have a reference. Okay, yeah. Either VI is greater than RF or VI is less than RF. That depends on what is sent in as VI. Okay, so VREF is actually maintained at a certain voltage. All right, reference. So supply voltage here given positive Vs is 20, negative Vs is minus 20. Yeah, okay. Of course, just now based on what we just went through, we look at the condition to determine the output here. All right. So they ask you to check what is the following output if V1 is 5.8 volts. All right. VN. Okay. So the reference voltage is first of all 5 volts. Reference, this fixed one, this one don't change. Okay, it's coming from here. Okay, the reference voltage. Okay, now then your VI will change because the voltage will fluctuate, go up or go down, but compare with the VREF. So the first question, they say A, or what is VO if VI is 5.2 volts? So straight away, we apply this condition, we check what happened. They say VI, or rather the input is greater than the VREF, which is true. It's 5.2 volts greater than 5 volts. And then what will happen at the output? The output will be equal to Vs, and Vs is minus 20 volts. So in other words, your V out now is minus 20 volts. Are you okay? Be careful, the condition. They say VI is greater than V reference, which is correct, 5.2 volts now. Okay, 5.2 volts, I'm looking at 5.2 greater than 5. So output will be negative Vs, which is negative 20 volts. This one will come to the output. Yeah, will go to the output. Yeah. So the next one, they say now input is 4.8 volts. So you know that 4.8 volts is less than 5 volts. The condition again, right? So if it's less than your output, they already tell you that it will be equal to 20 volts, which is your Vs, right? 20 volts, not negative, 20. So this 20 will now appear at the output. Okay? Okay? So, in other words, to summarize, the first condition will appear at output when Vi is greater than the V reference, okay, which is correct. 5.2 is greater than 5 volts. So I will get negative minus 20 volts. Second condition, input less than, which is true, 4.8 is less than 5. Then your V out will be positive 20 volts. Okay, stop for a short while. Any question? Any question for the example? Okay, you know, then I move on. Okay, so example 5, they want you to do some drawing. Okay, so example 5, we continue as a comparator, but now they use it to so-called for another application. All right. Okay, so input, or rather the reference voltage given is 2 volts. Okay, which is here, right? Supply, yes, positive 12. Supply, negative 12, and output is here. Right. So based on the diagram, what happened? Let's take a look. So the reference voltage is here, 2 volts. And this is your input voltage. That means this signal is coming here. Yeah, it's coming here. All right. So when you go through the comparator, somehow the waveform changes. All right, now they show you. So when it's below the reference, it's going down. The moment it's going up here, this point, above the reference, it starts to go up. Yeah, negative voltage. Remember the condition? When the Vi is greater than your Vref, you get a negative voltage, right? Which is this part. I just circle. Okay, and then it stays there, right? Because it's all here. This part are all above 2 volts. Okay, this whole part of the signal. So it will be 0 here, or rather negative 12 volt. You'll get at the output. So the moment this signal comes back to here, all right, what happened? Now the moment is below the reference voltage, that means Vi less than Vref, you have an output of positive 12 volt. And then that's why the voltage starts to goes up here again. All right, and then stay there. Okay, they will stay here the entire time. This part. Okay, so that's why the condition is met here when V in is less than Vref, it will go to a positive voltage. And then it will stay there as long as it's above, or rather below the reference voltage, it will be a positive output. Okay? Then until it changes again, of course. But, right? Yeah. So this is how you get your waveform. Okay, you project down. Important point to note is a reference voltage. Okay. So in other words, this part is what? Vi is greater than Vi is greater than Vref. Okay. V reference. Okay. Right. So this one is opposite lah. This one is a Vi less than the Vref. Okay, which is actually coming from the condition we saw just now earlier on, the same thing. Okay? Pause for a short while in case some of you couldn't catch it. Any question regarding this waveform? Can you all understand it? If not, I can repeat, no problem. Just let me know. I can repeat the whole thing. Are you okay? So the main thing is, first of all, you look at comparator circuit, you must know the reference voltage first. What is given? After noting the reference voltage, we start to look at the input voltage because you want to compare the input voltage to the reference voltage. Yeah? And then depends on the condition, the output will change accordingly. Either positive supply voltage or negative supply voltage, which is shown here in the diagram. I mean the waveform here. Okay? So sometimes when you see this, the input is a sine wave, the output is like a square wave. We can call it the waveform changer, or yeah, okay, from sine wave to positive square wave. Okay, no question. Then we move further down. I think yeah, that is the end of your last topic. Okay. Um, any question as of now? Okay, this will be your last topic for AA. All right, I think it's in good time. Next week onwards, we will go on to do all the tutorials for revision for your final exams. Okay, and I will also post out the links, the earlier links of the video recording so that some of you may want to revisit it, right? Okay. Any question as of now? If not, maybe I think you can attempt the quiz 5 in my connection first. I think you haven't do quiz 5. So let me go and share the screen first. Go on. Okay, you can go on to attempt quiz 5 and then submit. Once you have done, you may log out from this session. All right. If there's any question, you can send by the message or you can speak to the mic. Thank you.